In this lecture you will get an introduction to VHDL. First we will briefly discuss the history of VHDL. We will then take a look at the structure of a VHDL source file and go through the different parts of it. Lastly, we will discuss objects and data types that you can use to describe your hardware in VHDL. So what is VHDL? VHDL stands for Very High Speed Integrated Circuit Hardware Description Language. It was invented by the US Department of Defense during the 1980s, and the purpose was to get a unified way of document hardware, especially ASICs. And this documentation also include things like delays of signals. Later on, tools were developed that made it possible to run simulations out of these descriptions, so people could actually simulate designs before they were manufactured. And a bit after that, tools for synthesis were also developed, which could create hardware from the documentation. Now VHDL is a rather rich language, but only a small subset of VHDL can be used to synthesize hardware, so keep this in mind if you find some code online. So we will start with taking a look at the structure of VHDL. A source file in VHDL consists of different parts. We have the library. Here we can make use of predefined types. We can also put previous designs into a library and reuse them later on. We have the entity that describes the module viewed from the outside. The architecture describes the logic inside the module. We have the package declaration and body, and this we can use to declare commonly used data types and functions that can then be used across multiple modules. And last we have the configuration, which allows us to have multiple architectures tied to a single entity, and then we can choose which architecture we would like to use at the moment. So we will go through library, entity and architecture in the following slides. We will not discuss package declaration, package body and configuration, as the intention of these lectures is to give basic knowledge of VHDL. The last three are a bit more advanced features. VHDL is a text-based hardware description language. So that is, we input our description in plain text. So this is the basic skeleton of a VHDL source file. First we have the library part. In this case we include a library IEEE, and then we make use of some of the features in this library. Then we have the entity, which describes the circuit viewed from the outside of this module. And we have the architecture that describes the behavior of the circuit, that is the logic inside the circuit or module. So one thing to know about VHDL is that it's not case sensitive. So it doesn't matter if you use capital letters or not. The library section of a VHDL source file allows us to reuse digital circuit that we had previously described in VHDL. We can also make use of predefined data types and functions by including them in the library section. The standardization organization IEEE has developed several packages which you can make use of when describing digital circuits in VHDL. The two most useful are STD Logic 1164 and Numeric STD. To make use of a library, you first invoke the library with the keyword library and then the library name. So here we have library IEEE. Then we must tell which part of the library we would like to use. So here we would like to use the std_logic_1164, and we would like to include everything in this library. So we put .all at the end of the line. So the library in VHDL is a bit like the hashtag include used when programming in C. In the entity part of a VHDL source file, we describe the external interface of the module. So this includes the name of the module, the inputs to the module, the outputs to the module, and we can also make use of parameterization in the entity, but this will not be covered in this lecture as it is a bit more advanced features. We will now take a look on how we can describe the entity of this circuit in VHDL. So this circuit has two inputs, A and B, and one output, Q. And the name of the module is circuit 1. So we start by using the keyword entity, followed by the name of the module, which is circuit 1. And then we make use of the keyword port to declare the inputs and the outputs to this circuit. So we have that A and B are inputs to this circuit, and O is output of this circuit. In the last row, we end the entity declaration by using the end keyword, followed by the circuit name. So the declaration of inputs and outputs follow a certain pattern. So first we have the name of the input or output, in this case A. Then we have a colon, and then we specify which direction this signal flow. So this can be in, out, or in-out. The in-out will not be covered in these lectures. For the signals declared as in, they are read-only inside this circuit, so we cannot assign values to an input signal. Similarly, outputs cannot be read by the circuit. We can only write signal values to an output. In the architecture part of a VHDL source file, we describe the internal operation of the circuit. And this can be done in two different ways. We can describe the behavior of the signal, that is how signal values are generated. Or we can use subcomponents and then specify how these components should be connected together. Or we can do a mix of these two. So the syntax for the architecture part is like this. First we use the keyword architecture. Then we give a name of the architecture, in this case A_circuit 1. And then we tell which entity this architecture belongs to. So in this case it belongs to the circuit 1 entity. At the next row we can declare internal signals in the circuit. So in this case we need a signal to describe the wire between the NOT gate and the OR gate. So we call this signal C. And the keyword signal will be explained in the next slide. Then comes the keyword begin, and after this point we describe how signals are generated and how subcomponents are connected together. So all these statements are concurrent statements. That means they all run in parallel, so the order doesn't matter. This is a description of how the circuit looks. So the signal C is the inverted version of A, and Q is B or C. And then in the last row we end the architecture with the keyword end and then the name of the architecture. So if we take a closer look at one of the concurrent statements, we have that C is in this case assigned the value of not A, and the angle bracket and equal sign is used to assign values in VHDL. And then we end the row with a semicolon. In the previous slide you saw that we made use of the keyword signal. A signal is an object in VHDL, and an object is a named item that holds a value of a certain data type. In VHDL we can make use of 4 different objects. We have signal, constant, variable, and file. A signal can be viewed as a wire in hardware, or even a wire with memory, that is a wire connected to a flip-flop. A constant can be viewed as a wire with a constant value in hardware, so it can be like a wire connected to a logic high or logic low, for example. The variable is a bit tricky, and depending on how you structure your VHDL code, it can sometimes be viewed as hardware, but this is highly depending on how you describe your circuit. And I know that there are a lot of examples online that use the variable to describe logic circuits, but I recommend you not to do this. There's really no benefit of using variable instead of signal. So I would recommend you to stick with a signal object, as this is more clear what it translates to into hardware. Lastly, we have the file object, and this cannot really be used for synthesizing hardware, but it might be quite handy when you write test benches for testing your circuits. So when you describe hardware circuits, you will more or less only use the signal and constant object. We will take a closer look at the two objects, signal and constant, and we start with the signal. So first, everything that you specify under the entity part of your VHDL description will be of the type signal. So A, B and O will all three be of the type signal. Also remember that we specify the direction in the entity part. So A and B is input to the circuit. This means that we can only read the value of A and B. We cannot write the value to A and B. And opposite, O is the output of our circuit. So this one we can only write the value to. We cannot read it. We can also declare signals under the architecture part of our VHDL source file. So this we do before the keyword begin. So in this case we declare a signal C, and this is then an internal signal to this circuit, so we cannot read it from the outside. It is only available in the architecture part of our description. When we assign a value to a signal, we make use of the operator angle bracket and equal sign. So here we assign a value to C that is the inverse of A, and we end the statement with a semicolon. When you use signals in your description, they will more or less always be translated into a wire or a wire with memory when you synthesize your design. The other object that is often used in VHDL to describe hardware is the constant. A constant is an object that holds a value that cannot be changed. So you can think of this as a wire with a certain value that you cannot change in your hardware. And the benefit of using constant is that it can increase the readability and flexibility of your VHDL description. Constants we declare under the architecture part of our VHDL source file before the begin keyword. So here we declare a constant named active, and then we also must assign an initial value to this constant, and we do this with a colon equal sign and then the value 1. So now we can use this active in our description later on in this architecture, and this may make our description more readable, as the name active is more meaningful than a logic 1. When declaring signals in the architecture part, we can also assign initial value to the signals, and the syntax is similar, but here we use the keyword signal instead of constant. However, many physical devices cannot implement this statement. That is, they cannot generate a wire with an initial value. But this statement can be quite handy when you write test benches where you would like to have initial values of your signals before the simulation starts. We will discuss two more things in this lecture, and that is data types in VHDL and operators. VHDL contains around 12 predefined data types, but only a few set of this is relevant for synthesis. As you might remember, in the beginning we mentioned that VHDL from the beginning was meant to document hardware. Only a small subset of VHDL can be used to generate hardware. So predefined data types that we may use in our description is an integer, which can hold both positive and negative values. We have the Boolean, which can be true or false, and we have a bit that can be either a 0 or a 1, and a bit vector, which is an array of bits. So one thing to note here is that the bit, we specified a 0 enclosed in single quotes. If we do not do this, it will be interpreted as an integer instead. But to better reflect real hardware, IEEE introduced the two new data types, the STD logic and the STD logic vector. So the intention of this data type is that they behave more like real wires in hardware. So the STD logic can take on a number of values. We have the U, X, 0, 1, Z, W, L, H, and dash. 1 and 0 stands for logic high and logic low. Z stands for high impedance. L and H stands for weak logic low and weak logic high. X and W stands for unknown and weak unknown. And U stands for uninitialized, and dash is the don't care. When you describe hardware, you will more or less always use 1 and 0 and sometimes Z. But when you run simulations, you will also see the U and X appearing. So if you have an uninitialized signal, the value U will appear in the simulation. Similar, if you have a short circuit, you will see the X appear. So a short circuit could be that, for example, you connect the output of two different gates together and then try to drive different values. This will then create a short circuit, and it can be detected in the simulation. To make use of the data type STD logic and STD logic vector, you must include the library IEEE, and then also specify that you would like to use the STD logic 1164. STD logic and STD logic vector are the data types that are preferred when you describe hardware, as they mimic the physical behavior of hardware wires. Last, I would like to point out that VHDL is a strongly typed language. So this means that you cannot assign an integer to an STD logic without doing a typecasting or using a typecast function. VHDL has around 30 operators that operate on different data types. And only a small set of these have been overloaded to work with the STD logic and STD logic vector, and that is the NOT, AND, OR, XOR, NAND, NOR, and XNOR. To control the precedence of these operators, I recommend that you use parentheses so you get the right logic expression. And lastly, to create a comment in VHDL, we use a double hyphen, and then we write our comment like this. In this lecture, we have gone through the basic structure of a VHDL source file, and we have also discussed different object types and data types. Lastly, I would like to give you some good to know about VHDL. So the first and most important thing to remember is that you are not writing software. So VHDL is used to describe hardware. Inherently, hardware is parallel, and so statements in VHDL are executed in parallel. So this means that the order of the statement doesn't matter. As compared if you write the program written in Java or C, the order does matter, but not in VHDL. I'll also recommend that you only use the object of type signal and constant, and that you use the data types STD logic and STD logic vector as much as possible.